As some of you now know, research projects can be very time-consuming and costly if funding is even available. So many students today often develop computer models and situations to test their ideas. However, for others, like Lieutenant Christopher and Miriam, a hands-on approach with a small-scale version provides tangible evidence in support of a large-scale experiment.
And about to drop. 3, 2, 1. My thesis work is essentially a stratified wake problem. We did some computer modeling, and I'm scaling up from the virtual world into the real world using a tank. What I've done in this tank is layered cold water at the bottom with warmer water floated on top. And what I'm trying to do is look for different perturbations in the wake that follow this little shuttle as it is pulled across the tank. So as it goes along this guide rod, it moves the water and causes internal waves, which sometimes reach the surface, and you can see that with reflections in the infrared spectrum, thermal spectrum. I need to know the temperature of the water at different levels, which is what I use this temperature probe for. I've got measurements marked every 5 centimeters with the temperature being taken at the very tip. So I can suspend this at different levels within the tank, take a measurement and raise it up and create a temperature profile. The higher the velocity, the larger the wake. To control the velocity, I've rigged up a tow line. I hang different amounts of weight from this hook and have it pull down. Heavier weight, faster speeds. To accurately measure the speed of the shuttle, I've attached a little foam ball to the line that passes through these photo gates, which are light gates. So there's a laser passing between each arm of the photo gates that, when broken, starts the timer and stops the timer respectively. That time readout is seen on this oscilloscope by the drops in the 2 photo gates in the signal. So I can see how much time had elapsed. Since I know the distance between the 2 photo gates, I can measure the time and then calculate the distance traveled over time, which is velocity. So as I mentioned before, I am looking at the surface of the water using an infrared camera, which detects heat. By looking from a top-down view, I'm able to see when the cold wake breaks the surface of the water. And at that point, I can see a thermal signature on the IR camera where it's a little blue plume amongst the orange and yellow colors. I also have an actual temperature readout, of course, for the more precise measurements. The next step, which we've already begun work on and designed some tow bodies, is to go out into Monterey Bay and look at real-world conditions, because those will vary quite a bit from tank work. There's exchanges of momentum, temperature, sound. All sorts of environmental conditions are constantly changing within the entire spectrum of deep water, at the surface, and above the surface. In here, it's a very controlled environment, whereas out in the bay itself, I can't control what the stratification level of the water is, how cold the deep water is, how warm the surface is. Ultimately, Mother Nature decides what the conditions will be. The ocean also drives the atmosphere. The sea surface temperature has a huge impact on precipitation levels. Everyone is familiar with El Nino, where warm temperatures in the Western Pacific kind of slosh back to the Eastern Pacific. As we understand how that mechanism works, we're better able to tune atmospheric models as well as oceanographic models. So the more we know about this process, the better we can develop models that will predict the conditions of the ocean.